All right, so here we're going to talk about the VSEPR theory of molecular geometry, really just a fancy way of saying the theory that allows us to get to predicting these molecular geometries. What VSEPR theory really is, it stands for valence shell electron pair repulsion theory. What it means is that these hybridized orbitals that form, they want to form as far away from one another as possible. The real key word here is repulsion, right? So this is a theory that these molecular geometries arise because the bonds that are in these orbitals want to be as far apart as possible. So that means that we have to pay attention to the hybridization in order to get at the geometry of a molecule. Specifically, right now we're looking at, this is going to be electron geometry. So the geometry that the electron, of where the electrons are sitting. So when you have an sp hybridized molecule, those sp lobes that form, I guess that's kind of confusing. When you have an sp hybridized molecule, those new orbitals that form want to be as far away from one another. So that's why those molecules form a linear shape or a linear electron geometry. When you have a trigonal planar, it turns out that the best way to arrange three things in space that are equally far from one another is to arrange them in a plane. Any kinking out of that plane will actually bring them closer together. And when you're sp3 hybridized and you have 4 of those bonding orbitals, the best way to arrange them in space to keep them as far apart as possible is what's called a tetrahedral. This is actually a shape that we are not very familiar with. This picture doesn't necessarily do it justice. This is where having a model kit is really, really nice. But it's essentially four of those bonds would be equally spaced at 109.5 degrees from one another. So that's this sort of very special shape in chemistry, a tetrahedral. So these would be the electron geometries. There's a one-to-one correspondence between the hybridization and the electron geometry. What I mean by that is if you know the hybridization, then you know the electron geometry. All right, so what the process is going to be is you're going to be given a molecular formula. You're going to have to first draw its Lewis structure following that procedure that we laid out in the Lewis structure video. Then you're going to have to be able to count steric number to get to hybridization, right? So this is what we did last video. So we have a 1, 2, 3, 4 steric number, which means that this carbon is sp3 hybridized. And now we have to learn this next part, which is that the hybridization and the electron geometry, there's that one-to-one correspondence. If we know the hybridization, we know the electron geometry. So that means, and then the last step for determining the molecular geometry, so this is electron, is to consider if any of those orbitals are actually occupied by lone pairs. In this case, they aren't, right? So for methane here, all 1, 2, 3, 4 of those bonds of those orbitals are bonds. So, you know, my hydrogen would all be located at either end here. So the actual molecular geometry is a tetrahedral. Right, so this is how we would determine that for methane, molecular geometry is the same as its electron geometry, it's a tetrahedral. But now let's take another example. Here we have ammonia. Ammonia also has a steric number of 4, because that lone pair also counts as a +1. So it's also sp3 hybridized. So its electrons are also arranged in this tetrahedral here. But the hydrogens actually only lie at 3 of those bonds. This one here is only housing that lone pair of electrons. There's not a bond in there. So the molecular geometry of this one, considering the fact that there isn't a bond, is going to be different from the tetrahedral electron geometry. And this is what we call, whoops, trigonal pyramidal. Trigonal pyramidal. Okay, and again, it would really help to have a model kit in front of you. You could take your tetrahedral that you built and you pop off one of those bonds, and what you see sitting there in front of you is this trigonal based pyramid. It's not very high, but nonetheless, they don't all lie in the same plane. So that's why it's pyramidal. So just to sort of image those real quick, take a look at, there's another possibility with water where actually 2 of those orbitals are now occupied by lone pairs. And so that changes the molecular geometry to bent, different from the tetrahedral. Okay, but these are the classic 4 sp3 geometries: methane, ammonia, and water. They all share the same steric number, all share the same hybridization. But in terms of lone pairs, methane has 0, ammonia has 1, and water has 2. Okay. Another thing I want to point out about this is this drawing right here and what these wedges and dashes mean. This is what's called a perspective drawing. It's trying to convey geometry through just the 2D printed page. So what it's meant to sort of represent is that these sticks, these wedges rather, they're pointing out of the page. So when you see that, you want to imagine that it's pointing out towards you. Different from these straight lines here. These straight lines, these are in the plane of the page. And then lastly is the dashed lines. This is meant to be pointing the other way, pointing into the page. Okay, so same with water over there. And again, the shape for ammonia, we call that a trigonal pyramidal, and the shape for water is bent. Okay, so there's this little flow chart that you can think of. This is sort of the procedure of starting with a Lewis structure, going through steric number, hybridization, and then finally getting, this is actually backwards. I'm just realizing this should be electron, and this is molecular. All right, I'll have to change those in the notes. But yes, so if you're sp3, you can either be tetrahedral, trigonal pyramidal, or bent. sp2, trigonal planar with no lone pairs if you have 1 lone pair. So that would be as if I got rid of this bond here. This is also considered to be bent. And then sp hybridized are linear. So there's one more concept we got to talk about with regard to this molecular shape. Yeah, the fact that we now know that molecules have 3D shapes, we can build off this idea of bond polarity, right? So remember, we talked about bond polarity and how that has to do with the difference in electronegativity between atoms. So if we take a look at this molecule here, chloromethane, the carbon-chlorine bond is a polar bond, meaning there's more electron density up here than on my carbon atom. So now we're going to talk about molecular polarity, meaning does the molecule as a whole have one of those dipole moments? In this case, because carbon-hydrogen bonds are nonpolar, there is a dipole moment that runs all the way through that atom, meaning that on one side of the atom, there's more electron density than the other. If you have more than one polar bond, then it's like you take these arrows and add them up. That concept might sound weird, adding arrows, but it's actually what a real concept called vectors that you will learn at some point in your chemistry career. We're not going to do it mathematically, but nonetheless, in this case, these 2 bonds, these vectors would add up, and the new vector would be pointing right down the middle of the 2 of them. And so what this is saying is that in this molecule here, there's this region of high electron density over here and a region of low electron density over here. We would say that there is a dipole moment associated with this molecule. This is going to have important repercussions when we talk about how molecules interact with one another. Okay, but since we just talked about geometry, it's important to note that this is sort of a consequence of that. One other example I want to do real quick with this is what would happen if all 4 of these were carbon-chlorine bonds. This would be an example of a molecule that has polar bonds. All 4 of these bonds are polar. But because they're arranged equally in space, right, the angles between all those bonds are the same. They're the same distance apart, and they're all pointed in different directions. The net sum of those vectors would be 0. They would effectively all cancel each other out. So let me just change this over here. Right, so this would have no dipole moment. Okay, or would be a non-polar compound. Despite having polar bonds, it has a 0 molecular polarization, polaritivity. Other classic examples that we'll talk about, as well as dealing with something with lone pairs. Lone pairs are considered to be electron density, right? So in the case of ammonia, not only do you have polar bonds where the electron density points towards the nitrogen, you also have that lone pair with that partial negative charge. So the net dipole moment, this one would actually be, if I'm going to be good, this is a perspective drawing where that's a dash and this is a wedge, runs right through the middle of that molecule. Likewise, water with its 2 lone pairs and 2 polar bonds, there's a big dipole moment that runs right up the middle of that. And again, polarity is going to have everything to do with how molecules are interacting with one another. So once you draw your Lewis structure, you then figure out what your molecular geometry is by going through your hybridization. You then want to look at your molecule and see, does it have a dipole moment? That's kind of the last question to ask. Okay. And that will bring us to intermolecular forces, which is how molecules are interacting with one another, and will be our last topic. But first, make sure you know your molecular geometry. That's an important one.